All right. So we learned some few basic things about MLP, multi-layer perceptron. Now we are going to expand that knowledge. So between single layer perceptron and multi-layer perceptron, the difference is, so here in single layer perceptron, you have only one neuron here. Okay, only one neuron that is going to take do the multiplication and give you the output. That is single layer perceptron. But for multi-layer perceptron, you have multiple hidden layers. That means just like our brains. Okay, so you have multiple layers. In first layer you have four neurons. Each circle you see here is a neuron. So four neurons in the input. That means this input layer can accept four columns of data in one go. Okay, first column is x1, second column is x2, third column is x3, fourth column is x4. So it can accept four columns of data. So input layer you should see at your data frame how much features you are going to use. So many input layers, neurons have to be set. Remember that. Okay, so this is input layer. And hidden layer, either you can increase or decrease. This is something that you have to experiment with. There is no hardcore rule wherein which you can say so many layers of neuron should be there in the hidden layer 1, hidden layer 2, hidden layer 3, hidden layer 4. There is no hardcore rule for that. Luckily for us, researchers have already done that. So we can only borrow their research work and use hidden layer. How many neurons should be in hidden layer 1, how many neurons should be in hidden layer 2, 3 and 4, etc. Finally, output also depends on what you are trying to solve. If it is a binary classification, then there should be only one output. Okay, if it is a multi-class classification, there should be multiple outputs. Let's just say, for example, you want to do loan default prediction. If a person is going to get the loan or not, then you need only one value here. Either he'll get it or he'll not get it. Either it can be 1 or it can be 0. Okay, that's why you need only one output. But let's just say you want to classify the objects in an image. Let's just say there is a tree. Let's just there is a person walking in the image. There is a beach, there is a sun, there is a I don't know what not. So for that you need multiple outputs. So then your output will be more than one. Okay, input and output, you have to understand what you are trying to get as output and what you are trying to feed. How many columns of data you are feeding, that much will be input layers. These hidden layers, there is no hardcore rule as to how many hidden layers there should be. If there are too many hidden layer neurons, then the model will overfit. If there are too less of neurons, then the model will underfit. Okay, if there are too many layers and if there are too many layers and if there are too many neurons in each layer, the model will learn the noise. Okay, so that is where you have to tune it between overfitting and underfitting. You have to decide that. Okay, moving on, what is happening at each layer is what we are seeing here. At each node, see, nothing will happen in input layer. Input layer is only there to supply the x values and randomly initialize the w values, multiply them and pass it to the hidden layer. Actually nothing is happening at input layer. Input layer is only supplying x values. At hidden layer 1, okay, at hidden layer 1, what is happening? W randomly initialized values are multiplied with x values and bias is added to that, and activation function is adding all those things and passing the output to next hidden layer. So that means whatever was happening at a single perceptron layer, entire process is happening at each and every neuron in or each and every node at hidden layer 1. Everything is happening here, everything is happening here, everything is happening here, everything. So that way You understand now, right? This entire flow is happening at one single neuron. Again, it is generating certain output. That output is passed to here. Again, some randomly chosen W weights are taken, multiplied, some noise is added. Again, activation function is applied at this layer, and again one output is generated. Again, that output is taken here. Again, some randomly initialized weights are taken. Okay, bias is added, activation function is done, and again one output is generated. Again, that happens here also. Finally, certain output is generated. Now multiple outputs are coming here. Okay, as you can see, multiple outputs are coming here to this one. Here at output layer, either this same process happens, or a, a simple filtering happens, or major average is taken for certain problems. Okay, either average is taken or majority is taken basis on the type of problem, either for classification or regression. Okay, did you understand how this neural networks is working? At each and every node, this entire process is happening. Inputs are taken, random outputs are added. Okay, then biases are added to that. Activation function filters that out. It generates one single value. That single value is passed to next layer, and again there also the same process happens. Essentially, same process is happening at each and every node of these hidden layers. Finally, the output for classification is taken as majority value. For regression, average value is taken. Understood? Did you follow this process? Okay, and all this process is happening for one single epoch. One single epoch, all this process is happening. So like this, multiple epochs have to be done. Again, the output whatever you generated may not be the right output. Again, that output is sent back. Okay, so multiple epochs happen. Next, before we will again come back to this. Mhm. Yes, high compute environment, high memory is required. That's why neural networks are very compute intensive. Okay, that is the reason why these large language models, they have parameters. When they parameters, they are talking about these weights. Okay, these weights that they have initialized, that is what they are talking about. They have trillions of token parameters, and inputs are also in terabytes or petabytes, whatever. That's why their compute environment is huge. Weight is basically everything is huge. Just to run one model on top of that entire internet data or the data sets they have curated, they will run it for 3 months non-stop. Imagine, 3 months a supercomputer is running on the data to learn from the data. 3 months non-stop, 24 hours by 7. Imagine. So that much high compute intensive these large language models or whatever the neural networks are, generally in general they are very compute intensive. True. Okay, all right. So some assumptions we have to learn. First assumption is, although there is not exclusive key feature engineering, but there is some simple minor transformations that you have to do. One is normalization or standardization of the data has to be done. Okay, your that means what we are saying is, if I give, see, understand, first of all, like you rightly pointed out, there is a huge computation. On top of that, if I give 1 million value here 1 trillion value, here 1 billion value, the computation time will further increase, right? Bigger numbers, multiplying time is more. Again, those storing those numbers memory is high, right? So everything will increase. That's why we have to bring down those values between 0 and 1. Okay, that's why we do normalization or standardization of the input data. That is mandatory. If I simply pass, that's why in this example you saw that we took values between 0 and 1. If you paid attention, I'm not sure if you paid attention here. That's why these values are between 0 and 1. They are not some 500, 5,000, 50,000, whatever. We have not taken those values because the computation will further increase. So the first assumption is the input data is already normalized or standardized. If it is not standardized, you have to standardize before feeding it to multi-layer perceptron. That is number one. Okay. Second thing is quality and quantity of data. Because these neural networks learn in the very similar way a linear regression learns, that means multiple times they have to learn, go back, correct the error, come back, and again go back, come back, error. So that to and fro motion is already there. I mean, to and fro processing is there. Hence, quantity of data should be huge so that the model can learn properly. And high quality of data should be there. That means no noise. If you paid attention, I gave the brightness level. Instead of giving brightness level for other cells as 0, somewhere in between I gave 10% also. Such noise can alter the output. Okay, so we have to make sure normalized data, quality and quantity of data should be high. Second one is independence of data. Same rule applies here also. Data samples that we have generated, they should be non-duplicate. One, they should be non-duplicate. Second thing should be, there should be not be much correlation between them. Independent features should be there. Okay, that is the second one. Third one is architecture design. Lucky for us, this is what I was talking about. Lucky for us, researchers, data science community has done immense effort. They have put in from across the world. Okay, they have put in a lot of effort and they have come up with right architectures that work for certain problems. This we need not worry because it's already taken care for us. Okay, what we have to decide is number of architecture design we have to come up with. Usually what we do is we have to decide number of layers, number of neurons that has to be chosen carefully, otherwise it may overfit or underfit. Okay, but what I'm saying is lucky for us, we don't have to worry about this. Okay, other folks have already done the job for us. Next is activation function. Suitable activation function has to be chosen for certain type of problem. This also you will find lot of help on the internet on how to decide which activation function should to be used for what type of problem. Okay, this also is taken care. Next one is learning process. This is where I was talking about that multiplying the reducing the weights by decreasing the product of weights into learning rate. So that is essentially the gradient descent algorithm only. This we already learned. Gradient descent algorithm is nothing but the algorithm wherein which you use a Hessian matrix, come up with a curvature of the matrix, then randomly initialize the m values. Now you decide how to go to the lower section of the curvature. Okay, so that we already learned. So that is what our optimization function is used here also. Okay, here also learning rate is used to converge the learning. Okay, to decrease the error rate. Okay, this process is exactly the same, no change. Loss function is also the same, no change again. For regression task, mean squared error or root mean squared error, mean absolute error, whatever we discussed yesterday, those metrics are used as loss functions. Loss function again determines how far away are your predicted values from the original values. That is what loss function is for. Okay, and cost function is also there. Cost function is the average of all the errors of the at each row level. If you calculate the error, it is loss function. If you take the entire average loss for the entire data set, then it becomes cost function. So for classification problem, we have cross entropy loss. This we will talk about in depth, okay, later on. And for regression, we have mean squared error. I think for regression you already know. Next is overfitting and regularization. Sometimes As you know, activation functions, if the result is in negative, it will make the answer as 0. Those neurons are not helping us, so we can do the dropout. Okay, that process we call it as regularization. Or we can sometimes, like I already showed you, the accuracy may increase and then start to decrease. Wherever it starts to decrease, we can stop the training process. Okay, if we have already reached the accuracy and it's not changing or it's going bad, decreasing, then we can stop. That process is called as early stopping. So such techniques are employed to improve the overfitting and underfitting. Next is cross validation function. Cross validation techniques can also be used. Nothing but if you use four nodes as training, one has to be validated. This we again will learn all these in feature engineering. I'm planning that as the next class. Okay, so there I will teach you everything on how to do the entire feature engineering and pre-processing and all of that. So in that class you will learn that. Next is computational resources. Okay, so we have to have huge CPU and GPU memory, compute clock cycle compute power, so that should be there. Okay, now these are all the assumptions. Next is advantages. Advantages is, I will start from here. Feature engineering, because MLPs learn the features by just matrix multiplication. You don't need to do manual feature engineering. You, whatever features you have, you just convert them between 0 and 1 and you feed it. As simple as that. You don't need to do lot of feature engineering process. That is the one big advantage for data scientists. Second thing is, automatically these MLPs can approximate the function. Nothing but they can learn what different patterns in the data. Okay, so you don't that's the reason why they can be the same MLP layer can be applied for image data also, text data also, audio signal also. You can change whatever the type of data, it will work. Non-linearity, see, linear regression, one of the biggest problem is if the data is non-linear, you can't apply linear regression. But that is not the case here. Just by changing this activation function, you can learn complex relationship in the data. So that is another advantage. It can be, even if the data is non-linear, you just change this activation function, it will automatically learn. So flexibility, you can use it for classification also, regression also, unsupervised also, clustering also. Everywhere you can use MLPs. Okay, next is adaptability. So it can be used now by taking this multi-layer perceptron. You can come up with your own different types of problems. For example, convolutional neural network, you can come up, recurrent neural network, again we'll talk about this. So these are mainly used for image and sequence processing, nothing but image data and text data, that like that you understand. So you can come up with LSTM models also. Okay, long short term memory, okay, models which can remember just like how our human brain remembers. Next is feature engineering. This we already talked about. These are some of the advantages. Disadvantages are computationally intensive model. That is we already discussed. Second is we have to set the hyperparameters like learning rate, number of neurons, number of layers. Okay, these are hyperparameters. These have to be set very carefully. Next is prone to overfitting. Sometimes it will learn noise also, not sometimes, most of the time it will do that. So we have to do dropout that we saw above, and we also have to do regularization that we saw to handle overfitting. Next is black box layer. Okay, black box nature. One of the biggest disadvantage is we don't know what, see, at one layer for one single MLP, maybe we can do some mathematics calculations and we can say, okay, this is what is happening. But when you combine thousands and hundreds of thousands of them, we don't know what is happening inside the entire architecture. Nobody knows how these are learning, but we know they are learning. Something like what happens to human brain also. One neuron you can explain what happens, okay, how it works, okay, it's releasing something, You can see, you can come up with some explanation here for one single neuron. Okay. But when you talk, when you combine millions of these, we don't know what exactly is happening. We know something is happening, but we don't know what is happening exactly. Okay, that is another disadvantage. It's a black box model. When you combine multiple layers of and multiple nodes of neural networks, you don't know what is happening. It's a black box layer. So even to this day, no one can properly say how these models are learning. Even the large language models they are talking about, they don't know how they learn. At least not in the, not at the overall overall they can explain you, okay, this is might be happening, but not exactly this is what is happening. So that's the problem. Okay. Next is, they need high quality data. If your data is garbage, it will give you the answer as garbage only. Okay, so that is another problem. And they require large amount of data, just like how babies learn. No, babies don't learn on the day one. If you say, if you show a toy and say this is a toy, you have to call it toy, baby won't call it toy, because it doesn't that's not how human brains learn, right? Over experience, if parents call it toy multiple times, now the baby learns, okay, there is some context, I also have to call this as toy, I have to play it with like this. Okay, from parents experience. So that same thing applies here also. You need large amounts of data. You can't just have one single data set, and in the very single epoch you can't make it learn. You have to feed the same epoch multiple times. I mean same data, multiple epochs have to be run. From that is what we call experience. Okay, so from that it can learn. Understood up until this point? Maybe they give a thumbs up. Okay, okay, all right. Next is, we'll see how it works on iris flower classification. So as you know, in iris flowers, okay, there are four different features, three different types of flowers. We call it virginica, okay, setosa, and there is one more, let's see, in the description it should be there. Yeah, here. So versicolor, setosa, virginica. So these are three types of flowers, iris flowers, and they have a certain petal length, petal width, okay, sepal length and sepal width. So sepal is kind of the tube that comes out of the flower. Petal is the actual flower, the petal, rose petal. You understand petal, right? So that one. So their width and length are measured. Basis on that, we have to classify. So don't worry about the code here, because this data set is already built into the sklearn. We are just loading that. And when you do petal length, so we are trying to plot sepal sample and petal sample. As you can see, three different variations can be observed. So for one color, based on a petal length is small for one species, okay, subspecies, and the red is for another subspecies, and the another color is for another subspecies. So this way you can identify petal length and sepal length. Next, what we are trying to do is, we are trying to identify, we are trying to run a scatter matrix to understand which features are giving us some correlation. So as you can see, sepal length has good, okay, sepal length is kindly distributed well. Okay, ignore the id column, ignore the first one. As you can see here, sepal width with sepal length, it's kind of there is one cluster here, but here it is mixed. But petal length, if you can see, one cluster is here, another we can divide it here, and the other one is here. So this way we can understand, you can separate the data basis on the features provided. So this is the data set. Okay, now we are looking at the distribution. The values are going from 2 to 4.5. Here the values are going from 1 to 7, and as you know, we have to compress these bit to 0 to 1. Okay, 0 to 1 we have to do, 4.5 to 8 here, 0 to 2.5. So we have to compress that. We will do that anyway. So as you can see, different rows are plotted. Okay, so here you can see, this is one This could be one subspecies, this could be another, this could be another. This way some variations are there, but sepal length is not a good differentiator factor between two subspecies. Here there is one, you can say, but here these two are more looking more or less the same for me. Anyway, uh, so we are just separating the data. Okay, we are separating the data just for plotting purposes. Okay, next we are gonna talk about the multi-layer perceptron. Now, one of the challenges we talked about is determining the weights. So in the first step, you will randomly initialize the weights. Okay, and the the weights have to be altered. Sometimes in some rows, the weights, just like how you saw here, right? The weights sometimes have to be made negative for certain x values. For certain x values, they have to made positive and increased. For a different x level, you have to modify the weights. Okay, that we have to do. How do we do? How do we do that is using a optimization algorithm. So here mostly used algorithms. Again, I'll explain these algorithms in depth in next class. There are multiple of them, but just for now, remember there is a optimization algorithm which will see. You know how this curvature has come, right? Using the Hessian matrix, you have come up with this curvature. Now on this curvature, you have to basically you have taken the cost function. If you feed it into the Hessian matrix, nothing but you calculate the second order partial derivatives of all that, you will get the curvature. In the curvature, you know which is the highest point, which is the lowest point, and from there you know how to where to move. Okay, so I mean the curvature may not exactly look like this, but it may be differ, which we saw in the previous class as well. But the idea is to come up with the slope values, that is the weight values for which the error is the lowest. So that is done by taken care by these optimization algorithm, momentum, RMS proc, Adam. Okay, so all these algorithm, most preferred algorithm is Adam. Okay, Adam optimizer. So again, I'll teach you in depth how these work in a simple way. That way you can remember. But for now, moving on. So this is what is happening. This is what I explained previously also. You take the inputs. In input layer, nothing happens. You just take the inputs. You pass these to first layer. In the first layer, what is happening is random weights are initialized and that are multiplied with inputs, and that summation is done. Some random number is added as noise, and the final activation will decide. Here there is activation also, that is not shown here. This one f1 is the activation function. Okay, that function will decide whether to pass whatever the value is being passed, whether to pass it as 0 or whether to pass it as 1. Okay, or whatever the value, positive value. So that will be passed here to the second layer, and that process repeats. Okay, so ultimately you will get the end result, something like this. So if it's 0, see, if it's 0, if the end result it has to pass to this one is 0, it won't pass. Okay, so this way it will remove that output. So randomly, how do they work? Initialize the random weights and biases with small randomized values, and then add those to the input layer until you get the output layer. This is called as forward propagation. This is what we learned in single layer perceptron. There is additional step. Now you have to update the weights. You have to update the weights because you have already calculated the error. You have to modify the weights and biases in the inner layers, and this process is called as back propagation, and this works basis on your differentiation. Derivatives are calculated. Okay, those derivatives we will talk about it, and this process is repeated until you get the result, satisfied result. Nothing but each time it goes, comes back, goes, comes back. So okay, that way forward and backward propagation is happening. Next is along this activation function calculation. So when you do, when you update the weights, you update the weights by multiplying this learning parameter to those weights. Okay, that is indicated with this derivative value. Okay, So you keep on decreasing until you reach the point where you have the minimum error value. When this value decreases here, so there also error decreases. Both are interlinked. So these are the activation functions, some of the activation functions that we can use. Sigmoid you already know. This is what you used in logistic regression. And this compresses the values between 0 to 1. As you can see on the y-axis, the values are between 0 to 1. Okay. Next is tan h. Tan h compresses the values between 1 and -1. Okay. Whatever is below 0, then that is taken as 0. Whatever above is 0 is taken as 1. Here that is not the case. Okay. Here 0.5 is the threshold value. Here 0 is the threshold value. ReLU on the other hand is you give any value above 0. On the x-axis you see this line is going on the x-axis. You project it. Any value above 0 will be taken as positive. Any value below 0 is negative, 0 only. Okay, it is 0 only. That's why the line is on x-axis 0. Okay, y value for that line is 0. So that's why it's 0. Now there are some variations of this ReLU. Okay, the ReLU variations is wherever it is less than 0, now they are not making it as exactly 0, it is rather making it as 10%, 0.1 of x, 10% weight they are applying. Okay, this solves one problem. Okay, vanishing gradient problem. Okay, so there are multiple concepts I will explain you in next class. Okay, so that is why they are using leaky ReLU. And LU is max out is the max value. You don't consider anything. Whatever the max value is there, you're gonna consider the max value only. This is used in making the images either blurrer or sharper. Max out. That also I will show you as interactive demo. That is very interesting. Okay. Next is LU. LU is a variation of the ReLU. Here, if it is x, it is considered as x greater than 0. See, the value between this and this is there is no sharp decline at 0. Here, if it is 0 at exact this point, okay, it is considered as 0 only. Less than 1, then it is 0.1 of x. To solve that problem, what they have done is they have made this as slight curve instead of making pointy. Nothing but at 0 point also it is going to consider certain value, this value. Although it looks complex to consider, but don't worry about it. So it is considering this one only. At 0 it is considering x value only. Here at 0 it is 0. Only if it is less than 0, then it is 0.1x. That is the difference between leaky ReLU and LU. So this way various activation functions are used. Okay. And to update, their derivatives are calculated using this one. Okay. What is the derivative of 1 by 1 plus np dot, that is exponential of minus x? So this one, x into 1 by x, 1 minus x. Okay, so these derivatives are calculated. Let's see. Hyperbolic ReLU. Okay, so in back propagation, this is a little confusing actually. So how in the propagation, forward propagation, you already know what happens. You understood it. In the back propagation, what happens is the output that you have obtained, that has to be modified because it's not the best output. So what you do is you start differentiating it. Differentiation, the same thing you learnt in 12th standard, you have to remember it. So differentiation is done. In differentiation process, some values are multiplied, some values are altered, and after altering, the error term is decreased by little bit. Okay, how they are done, this you can see it here only. So first what you do is you take the delta, means some small value. For that, what you are doing is you are multiplying with -1. You are multiplying with -1 into derivative of the weight. Some complex mathematics is happening. You can ignore this part, just understand the concept wise. Okay, and once you calculate that delta value, that is injected here, multiplied with learning parameter to decrease. This is what I was talking about. You take the weight, you decrease the weight by, if it is 0.5, you decrease, multiply it with 0.1, then you can decrease it to 0.45. Okay, 10% you can decrease. So that way this process happens for weights also. This process happens for bias term also. Weights are also updated the same way. Bias term is also updated the same way for all the rows. For all the outputs you have obtained, for them it is done. Okay, and then this process is called as back propagation. Finally the error is calculated the same way. Okay, so don't worry about the complex mathematics, just understand the in the back propagation, whatever the output you get, they are minorly modified by differentiating them and subtracting the product of learning rate into weights from the original weights. That way you can modify the weights. Okay, so there is a complete implementation of it here. So what is happening here, we have considered four layers. Okay, too many layer, sorry, input layer has four neurons. Okay, that means four inputs have to be taken. How have we decided on the four inputs? How did we decide this? Because we are trying to solve iris data. In iris data, as we already said, there are four features: sepal length, sepal width, petal length, petal width. So basis on that four feature, we have decided input has to be 4. Okay, how many hidden layers? 5. This is, you can experiment. There is no hardcore rule for this. Hidden layer you can experiment. Output layer, how many? 3. Why did we decide 3? Because there are 3 species of output. 3 species will get. Either it is Setosa, versicolor or virginica. So one of these 3. Learning rate also you can modify, you can change, you can see which one will give you. Here we have taken 600 times we are feeding the data. Not necessary, this is a big number, you can try with 100 first. Okay, or just for the sake of example we'll see. Next comes, see, is hidden value, is bias value, you ignore this. So next comes the activation function. How do you know which activation function to choose? See, very simple, we are doing the classification here, correct? For classification you have to choose sigmoid only. Okay, whether you are going to, again, okay, I will explain the activation functions, different activation functions, and then maybe you will understand it. So here activation function is chosen as sigmoid. Okay, and you can also choose one of these 3. Back propagation is implemented, the same thing that we just learned. So after implementing all of these, we are trying with various epoch values, nothing but we are doing the hyperparameter tuning here. We are trying to find which one will give you the best result. Upon basically we are trying with epoch values, we are trying with weight values. Okay, we are trying with activation functions, everything we are testing out. Upon doing the experiments, as you can see, the best one is number of epochs. See, accuracy increased up until this point. 500 was the epoch, 500 or 600. At 600 epoch, the value was maximum for node 5, and then after that it decreased. So as for this one also, the highest epoch value was at somewhere here. For this one also somewhere here. This way you can choose the epochs. Next is activation function. Activation function is, you have to decide how much error is being decreased. Maximum error decreased here only, 100 epochs. After that error did not increase much for a very long time, and then it decreased here at 400. After 400 it never decreased. So epoch 400 would have been the right one for hyperbolic tangent if you had considered. If you use sigmoid, then the epoch value is, I would choose 300, because not much, I have to shell down too much computation time just to reduce it from 0.05 to 0.03 maybe. Okay, so for ReLU is, notice 0.05 here, 100 epoch. So out of all these 3, which one do you think reduce the error very quickly? See, this one is reducing the error at 400. This one hyperbolic tangent is decreasing the error till here maybe, or maybe here, okay, 300. This one is 400. ReLU is decreasing quicker, no? ReLU is decreasing at 100 and then it is retaining. So I would go with ReLU. So activation functions also, as you can see, ReLU has been able to reduce it at much lower level. Okay. So basis on this, see, by doing what I'm showing you is how researchers have come up with answers. What is the best value? What is the best uh, activation function, and all of this. Basically, they do everything. They test it everything, and then decide which one is the best one. For us, we don't have to go through all these process. What we will do is rather is we will directly go to the problem solving. Multi object has no parameter params. Is there no else params of? Okay, anyway, we'll look at the data set. Anyway, moving on. So some error in the parameters. No time to debug now. Anyway, so moving on. So then finally after it does the forward propagation, backward propagation, it does the prediction part. Okay, how is the prediction done? It has already decided the weights. When a new value comes in, it simply multiplies the end result with the weights. Whatever the new value you have supplied, it multiplies that with the already determined weights. Once you determine, then again it passes it through the activation function and you'll get the output. A simple activation function is like a simple filter. Okay, so this way, as you can see here, outputs are decided, calculated. Okay, sometimes they could be incorrect also. That is where we calculate a lot of metrics. As you can see, 96.67% of the time it is able to classify correctly. 3.3% of the time it made the mistake. Basis on this, you can also do the calculation at you can come up with the confusion matrix, or you can do the accuracy at different level. So basically the least accurate flower was versicolor, and it makes sense also. Why? Because if you paid attention above, versicolor, when we plotted this, notice the see, first one is setusa, this one is setusa. Here with by petal width you are able to identify, but with sepal width, see, versicolor and virginica both have the same things. That's why the error rate is high here. Some might have been misclassified as versicolor, possible. Okay, so this way MLP does the classification. Okay, so you can calculate a lot other metrics to see how the model is doing. But for you, if you work on a problem using MLP, all you will do is you will call that MLP model. Okay, from sklearn you can call MLP. Once you call that MLP, you will just feed these values, x value. First you will do the transformation between 0 to 1, and then you will do the feeding of the. First you have to decide the layers also, how many layers you want, how many epochs and all of that, and then you will feed it. I will show you end-to-end full problem in the next class. This was just the basic example I chose to give you lay the simple foundation. But in next class I will show you end-to-end how it works for classification, how it works for regression, and also we will see what are the different concepts you have to learn. For example, vanishing gradient problem, that is a big problem. Okay, how it is solved, that we will discuss, and how to reduce the overfitting part. So various concepts are there, different activation functions. So all of that we'll learn in the next class. Okay, any doubts till here? Yeah. So as you can see here, we have run multiple epochs. Error was very high here, 88.9% actually. 8.9% was the error rate in the first epoch. As we ran 50 times, we after running we got 5% error. Then after running 400 times, 20%. And then after running 700 times, we got only 1.2% of error. And beyond this we can't further reduce. Okay, so this is the error. If you see MSE, it has decreased slowly till 700 for 700 epochs. And different neurons, we are calculating the weights, how they are learning. Initially randomly initialized, everyone started at minus, some of them started at -1, some started at 0.5 or 0.2 or something. One started at 1 point something. Okay, from those weights they kept on differing, and finally they reached this value, final weights. Okay, here also weight output update during training. This is during training. This is how the weights have changed. This is for output, this is for input. Okay, so this way they have changed. Some error is there, but anyway, it's fine. All right, I will